Welcome back. In this video, we're going to be looking at example problems of using integration by parts via the tabular method. Let's get to it. All right, so here's our first example. We have the integral of x to the fourth power times e to the power of 2x times dx. Now, when you want to use the tabular method for integration by parts, you want to start by drawing a table with two columns. One column will be labeled with d for derivative, and the other column will be labeled with I for integral. And so then what we want to do is look at our integral and determine what part of the integral we want to take the derivative of and what part we want to integrate. And this goes back to the original integration by parts formula where you pick a u and a dv from your integral. And so if you're not familiar with integration by parts, feel free to watch my lesson video on that first before attempting this tabular method. But in this case, we would want to set u equal to x to the fourth power and dv equal to e to the power of 2x dx. Now in this case, we're not going to explicitly use u and dv. Instead, we have these two columns of our table. But the term that we would set equal to u is going to start our derivative column because we take the derivative of u. And the part of our integral that we use for dv will start our integral column because we integrate dv in the traditional integration by parts method. And so if x to the fourth power will be u, then we'll write x to the fourth power to start off our derivative column, which means that e to the power of 2x is going to start our integral column. All right, and so then what we want to do is we want to take the derivative of our term in the derivative column, and we want to integrate our term in the integral column. And so let's take the derivative of x to the fourth power. And so if we do that by using the power rule for derivatives, we will have 4x cubed because we multiply the exponent down and then subtract 1 from that exponent. And then to integrate e to the power of 2x, that would typically require u substitution since we have a composite function. Right, we have e to the power of a function other than just x. We have 2x. But to keep things simple, we're going to use a little trick here that when you integrate e to the power of x, where that x is multiplied by some coefficient, the integral is just going to be that exponential function, e to the power of 2x, divided by that constant multiple that is multiplied by x. So we will divide by 2. Okay, so that's the integral of e to the power of 2x. And so then we're going to do that process again for our two new terms here. We'll take the derivative of 4x cubed, and we will integrate e to the power of 2x divided by 2. And we will continue to do that until we meet some kind of requirement that tells us to stop. And so here are the three different indicators or stops that will let us know when to stop adding rows to our table. The first stop is the simplest one. If either of our columns reaches the value of 0, then we know that we should stop filling in those terms, and then we can set up the solution to our integral. The second stop is if you notice that you have matching terms, meaning that the product of the terms in a row is a multiple of the original integrand. And we will see an example of that if that doesn't quite make sense yet. And then our third stop is if you see that the product of a row is easily integrated, meaning that if two terms next to each other in the table, meaning one from the derivative column and one from the integral column, if those two multiplied together can be integrated without integration by parts, then you want to stop taking the derivative and integrating your terms and then set up the solution to your integral. Again, we'll look at an example of that later on in this video. But if we go back to our first example here, in this case, if we continue to take the derivative of this algebraic expression, eventually we are going to reach 0 because the exponent of x is going to decrease by 1 every time we take the derivative until we reach a constant, and then ultimately the derivative of a constant is 0. And so if we continue on with our derivatives, the derivative of 4x cubed will be 12x squared because 3 times 4 is 12, and then subtract 1 from the exponent and you have 2. And then if we take the derivative again, we will have 24x because 2 times 12 is 24. And then if we subtract 1 from that exponent, we have x to the first power. And then if we take the derivative again, we will have 24 because the derivative of x to the first power will just be equal to its coefficient, which is 24. And then the derivative of 24 will be 0. All right, and so then what we want to do is we want to integrate this term up until that point so that we have filled both columns up until that final row where the derivative is 0. All right, and so if we take the integral of e to the power of 2x divided by 2, remember that the integral of e to the power of 2x will just be that same function, but divided by 2. And so we're just going to keep dividing by 2, and that denominator is going to increase by a factor of 2. And so the next integral will be e to the power of 2x divided by 4, because we're dividing this by 2. So 2 times 2 will be 4. All right, but I'm going to start running out of room here pretty quick. So to condense this a little bit, I'm going to rewrite each of these terms as just being 1/2 times e to the power of 2x and 1/4 times e to the power of 2x. And then we'll continue on from there by just multiplying by 1/2 instead. It's the same as dividing by 2. And so let me just rewrite these. We're going to have 1/2 times e to the power of 2x. Then we'll have 1/4 times e to the power of 2x. And then if we continue to integrate, we're just going to keep multiplying our previous integral by 1/2. So we'll have 1/8 times e to the power of 2x, then 1/16 times e to the power of 2x, and then 1/32 times e to the power of 2x. Okay, and so now we have filled in our table, and so now we're almost ready to set up the solution to this integral. One more thing we need to do is add some signs along our derivative column. And we'll start with a plus sign, and then we'll alternate between a negative sign and a plus sign. So we'll have negative, and then plus, and then negative, and then plus, and then negative. Okay? And now what we're going to do is we're going to use this table to set up the solution to this integral. And so this integral will be equal to the first term in our derivative column times the second term of the integral column. And so what we're going to be doing is adding up the terms that you get by multiplying diagonally like this. All right, so what we're going to have for our first term is positive x to the fourth power times 1/2 times e to the power of 2x. So we'll have x to the fourth times 1/2 times e to the power of 2x. Then our next term will be negative 4x cubed times 1/4 times e to the power of 2x. So we'll have minus 4x cubed times 1/4 times e to the power of 2x. And then our next term will be positive 12x squared times 1/8 times e to the power of 2x. So we'll have plus 12x squared times 1/8 times e to the power of 2x. Then I'll write my next term down here, and that will be negative 24x times 1/16 times e to the power of 2x. So we'll have negative 24x times 1/16 times e to the power of 2x. And then our last term is going to be positive 24 times 1/32 times e to the power of 2x. And so we will have plus 24 times 1/32 times e to the power of 2x. All right, and then one more thing that we don't want to forget is to add plus c to the end of our solution. All right, and so this would be the answer to this integral. However, we can simplify it a little bit. Notice that this 4 and this 4 will cancel out. And then 12 divided by 8 will reduce to 3/2. 24 divided by 16 will also reduce to 3/2. And then 24/32 will reduce to 3/4. So our final answer is that this integral is equal to x to the fourth power times e to the power of 2x divided by 2 minus x cubed times e to the power of 2x plus 3 times x squared times e to the power of 2x divided by 2 minus 3x times e to the power of 2x divided by 2 plus 3 times e to the power of 2x divided by 4 plus c. All right, and so what we have right here is the solution to this integral. This is the antiderivative of that function. For our next example, we have the integral of x cubed times sine of 5x dx. And so if we want to integrate this using integration by parts, or more specifically, the tabular method for integration by parts, we want to start by drawing our table. So I'll do that, and we're going to have two columns. We'll have the d column and the I column. And so the parts for this integral that we are interested in is this x cubed, or this algebraic part, and then this trigonometric part, sine of 5x. And so when you have an algebraic part times a trigonometric part, you're going to want to set your x part equal to u if you're using the traditional integration by parts method. But in this case, that just means that we are going to be taking the derivative of x cubed, and we will integrate the trig function sine of 5x. So we'll set up our table like this. we're going to have x cubed and then sine of 5x. Okay, and so similar to our previous example, note that if we keep taking the derivative of an algebraic function like x cubed, we are eventually going to reach 0, and so we know that we can stop filling in this table once we reach that 0. And so let's work on that first. Let's take the derivative of x cubed. That will be equal to 3x squared if we use the power rule. We multiply 3 down and subtract 1 from the exponent. Then if we take the derivative again, we will have 6x, because 2 times 3 is 6, subtract 1 from the exponent, you have a power of 1, and then the derivative of 6x will just be 6, and the derivative of 6 is 0. Alright, and so now let's integrate sine of 5x. And similar to our previous example with e to the power of 2x, we have another composite function that we would typically integrate with u substitution. But there is a little trick here once again. Since we have sine of 5 times x, right, just some constant multiple times x, the integral of this function will be the integral of sine with the same inside function, and then we will divide by that constant multiple of 5. So we will divide by 5, or in other words, multiply by 1/5. And so the integral of sine is negative cosine, so we will have negative cosine of 5x, and that will be multiplied by 1/5. Which is the same as dividing by 5. And then if we integrate again, the integral of cosine is sine, so we'll have negative sine of 5x, and we're still multiplying by that 1/5, but now we need to divide by 5 again, so we multiply by another 1/5, and so 1/5 times 1/5 is 1/25, so I'll rewrite that to have 1 divided by 25. And then if we integrate again, the integral of sine is negative cosine, so now that negative is going to cancel out with that new negative. So we're just going to have positive cosine of 5x times 1/25. But once again, we need to multiply by another 1/5 or divide by another 5. And so 1/25 times 1/5 will be 1 divided by 125. So we'll have 1 divided by 125. And then if we integrate one more time, the integral of cosine is sine. So we will have sine of 5x times 1 divided by 125 times 1/5, which will be 1 divided by 625. All right, and so now we have one more thing to do. We just need to add our signs along our derivative column. So we have plus, then minus, then plus, then minus, then plus. Okay, now we can start setting up the solution to this integral. We will be multiplying our terms diagonally and adding them together. And so if we start with our first term, we'll have positive x cubed times negative cosine of 5x times 1/5. So our integral will be equal to x cubed times negative cosine of 5x times 1/5. And then our next term will be negative 3x squared times negative sine of 5x times 1/25. And those two negatives are going to cancel out. So we will have plus 3x squared times sine of 5x times 1 divided by 25. And then our next term I will write down here, and that will be equal to positive 6x times cosine of 5x times 1 divided by 125. So we'll have plus 6x times cosine of 5x times 1 divided by 125. And then our last term will be negative 6 times sine of 5x times 1 divided by 625. And so we will have minus 6 times sine of 5x times 1 divided by 625. Okay, and then you don't want to forget to add plus c to the end of that solution. And so you could leave your answer like this if you wanted to, but I'm just going to rewrite it a little bit so that it looks a little bit nicer. And so we'll have that this is equal to negative x cubed times cosine of 5x divided by 5, right? I move this negative out front. So we have negative x cubed times cosine of 5x, and then I just put both of those terms over 5, and so we multiplied them by 1/5. All right, and so I'm going to do the same thing for the rest of these terms. So we'll have plus 3x squared times sine of 5x divided by 25, plus 6x times cosine of 5x divided by 125, minus 6 times sine of 5x divided by 625, and then plus c. All right, and so that is the solution to this integral. So here's our next example. We want to find the integral of e to the power of 4x times cosine x dx. And so once again, let's start by drawing our table so that we can use the tabular method. We're going to have two columns. We'll have the d column and the I column for derivative and integral. And in this case, we have an exponential part times a trig part. And so in this case, it's not going to matter which one we choose to be in the derivative column and which one we choose to be in the integral column. You will still get a correct answer, but I'm going to choose to put the exponential part in our derivative column and the trig part, or cosine, in our integral column. And so we'll have e to the power of 4x in the derivative column and cosine x in the integral column. All right, and so let's take the derivative of e to the power of 4x and let's integrate cosine. And so if we do that, the derivative of e to the power of 4x is going to require the chain rule, since we have e to the power of some function other than just x. And so in this case, the derivative will be that function, e to the power of 4x, times the derivative of that inside function. And the derivative of 4x is just 4, so we'll multiply that by 4. Okay? And then the integral of cosine is sine, so we'll have sine x. And now we could do that again, and you're going to start to notice a pattern. So if we take the derivative again of this term, we're going to have 4 times e to the power of 4x, but then we need to multiply by the derivative of 4x again, and so we will multiply by another 4, and so this 4 will become 16, because 4 times 4 is 16. And then if we integrate sine x, we will get negative cosine x. All right, and so then we can continue to take the derivative and integrate here, but notice that neither of these columns are going to reach 0. Right, if we keep taking the derivative of e to the power of 4x, it's just going to continue to be e to the power of 4x times some constant. And then if we integrate cosine of x, we're going to get back sine of x, and so it's just going to alternate between sine and cosine. And so neither of these columns will reach 0, which means we can't use that first stop from earlier. Instead, we are going to have to use one of the other two stops. And one of them is if we see a matching term. And this is going to be very common when you have an integral of an exponential function times a trig function. If you look at your columns and there is a row that if you multiplied them together and it is a multiple of what is in your integral, then you want to stop at that row. And so if you look at our bottom row here, we have 16 times e to the power of 4x times negative cosine of x. If we multiply those together, we'll have negative 16 times e to the power of 4x times cosine x. That's just what we have up here in this integral, but multiplied by negative 16. And so this is a matching term, or a multiple of what we started with. And so we are going to stop right here. Okay, and so let's add in our signs next to our derivative column. We'll have plus, minus, plus, and then we're going to continue as we did previously. We're going to multiply diagonally, but then since our last derivative term is not 0, we're also going to multiply the bottom two terms and integrate them. That's going to be our last term. And so here's what that looks like. This integral will be equal to positive e to the power of 4x times sine x. So we'll have e to the power of 4x times sine x. And then our next term will be negative 4 times e to the power of 4x times negative cosine x. And so those negatives will cancel out, and we will be adding 4 times e to the power of 4x times cosine x. And then the last term will be the bottom two parts multiplied together and integrated. So we have negative cosine of x times positive 16 times e to the power of 4x, which means that we will add the integral of negative cosine x times 16 times e to the power of 4x dx. And so if we simplify, this will be equal to e to the power of 4x times sine x plus 4 times e to the power of 4x times cosine x. And then if we pull out this negative and this 16 to the outside of the integral, we'll have minus 16 times the integral of e to the power of 4x times cosine x dx. Right, I just reordered the multiplication here. Instead of having cosine times e to the power 4x, we have e to the power 4x times cosine x. It's the same thing either way. But now notice that this integral right here, the integral of e to the power 4x times cosine x, is the same as what we started with. It's just multiplied by negative 16. And so these are like integrals. And remember that this integral is equal to these terms. And so if I write that in here, the integral of e to the power of 4x times cosine x dx, we can combine those like terms or like integrals by adding 16 of those integrals to both sides of the equation. And so if we do that, we'll have one integral plus 16 of them, which gives us 17 times the integral of e to the power of 4x times cosine x dx. And that will be equal to e to the power of 4x times sine x plus 4 times e to the power of 4x times cosine x. Okay, so since we added 16 of these integrals to both sides of the equation, this is canceled out, and this one integral becomes 17 of them. And now, if we divide both sides by 17, we will have solved for the solution to this integral, which is the same integral that we started with. And so if we divide both sides by 17, the integral of e to the power of 4x times cosine x dx is equal to e to the power of 4x times sine x divided by 17 plus 4 times e to the power of 4x times cosine x divided by 17, and then don't forget your plus c to finish off the solution. And so this is the answer to this integral. All right, so just be aware that your table is not always going to reach 0 in one of the columns, and so you need to be on the lookout for a matching term or a product of two terms in a row that is a multiple of the integral that you started with, so that you can write the integral of those terms and then combine like integrals to get your final solution. Let's look at one more example for this video. All right, so here's our last example. We have the integral of the natural log of x divided by x cubed times dx. And so if we want to integrate this using the tabular method, I'll start by drawing our table. And so we have the derivative column and the integral column. Now in this case, I'm going to rewrite this integral a little bit. We can move this x to the third power to the numerator by making that exponent negative. And so this is equal to the integral of x to the negative third power times the natural log of x dx. And so now we can more easily see what the two parts are that we're going to be dealing with here. And in this case, since we have an algebraic part times a logarithmic part, we're going to make the logarithmic part the starting point for our derivative column, and then the algebraic part will go to the integral column. Okay, so that's all based on how we choose u and dv from the regular integration by parts method, which you're hopefully familiar with by now. If not, once again, feel free to check out my lesson on that topic. But in this case, we will have the natural log of x in the derivative column and x to the negative third power in the integral column. All right, and so let's start by taking the derivative of the natural log of x, and then we will integrate x to the negative third power. So the derivative of the natural log of x is 1 divided by x, and the integral of x to the negative third power, if we use the power rule of integration, by adding 1 to the exponent and then dividing by that new exponent, we will have x to the negative second power divided by negative 2. All right, and so now I'm going to stop there, because if you remember from our 3 stops, one of them, I believe the third one in particular, says that we can stop if we see that a product across a row is something that is easily integrated. And so if you take a look at what we have right here in the bottom of our table, we don't even need to take the derivative or integrate another time. 1 divided by x times this expression is going to be easily integrated, right? Because we could rewrite 1 divided by x to be x to the negative first power, right? Those are two equal expressions. And so if you multiply x to the negative first power by x to the negative second power divided by negative 2, the product will be x to the negative third power divided by negative 2 because you add the exponents, right? Negative 1 plus negative 2 is negative 3. And so this is the product of these two terms in this row of our table, and we can easily integrate this function. We know how to integrate x to a negative power. And so we can stop right there in our table and add our signs and then set up our solution. And so we'll have a plus and then a minus, and then we will multiply diagonally. And then for our last two terms, we will multiply them together and integrate them. And so our solution to this integral will be that it is equal to the positive natural log times x to the negative second power divided by negative 2. So we'll have the natural log of x times x to the negative second power divided by negative 2. And then we will add the integral of these two terms multiplied together. And so we have negative 1 divided by x times x to the negative second power divided by negative 2. This negative and that negative will cancel out, so we will have plus the integral of 1 divided by x times x to the negative second power divided by 2 times dx. Now if we pull this 1/2 to the outside and rewrite 1 divided by x to be x to the negative first power, then this is equal to the negative natural log of x divided by 2 times x squared, which is the same as this right here. I just moved x to the negative second power to the denominator, so we have x to the positive second power, and then I just move this negative to the numerator because it doesn't matter if that negative is in the numerator or the denominator, and so I chose to put it in the numerator. All right, and then we'll add that to that 1/2 taken outside of the integral times the integral of x to the negative first power times x to the negative second power dx. And x to the negative first power times x to the negative second power is x to the negative third power, so we have x to the negative third times dx. And then if we integrate using the power rule of integration by adding 1 to the exponent and then dividing by that new exponent, we will have that this is equal to the negative natural log of x divided by 2x squared plus 1/2 times x to the negative second power divided by negative 2 and then plus c. And then similar to how we rewrote this expression right here to this expression, we can move x to the negative second power to the denominator and move that negative out front. And that will give us our final answer that this is equal to the negative natural log of x divided by 2x squared minus 1 divided by 4 times x squared plus c, right? 2 times 2 is 4. We brought that negative out front and moved x to the negative second power to the denominator, so we have x to the positive second power. And so this is the final answer to this integral. And so that was the last example for this video on using the tabular method for integration by parts. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.